sinon je tomberai ma débite, rien ne restera qui ne soit pas vengé. Moi malheureux, que vais-je donc dire? Que vais-je donc dire?
Salvando salvas gratis, salva me fons pietatis, recordame, Iesu, que
Gemisco tamque abreos, culparum repentos meum, supplicanti parce Deus, qui Mariam absolvisti, Cantanem exaudisti, mi quaquis perdis. Preces me non sum digne, centuris frequenti, et perenni cremerinde. Interum est mundo presta, et abetis me segesta.
Santo nabis maledictis, flamis acribus pontificis, vacca mecum benedictis, salus sufflet, et acclinis, non contribum canestis, cere coram benedictis, lagrimas adversita, qualitus verdes maligna, iudicanto Deus, qui eterno parce Deus, piete Domine, data eis requiem.
All right. Guys, welcome to lecture 5 of MIT IAP 2025, Building Sound. So it's been a pretty fun week, but like we're doing 4 lectures this week, so it's been pretty fun. So we learned already about additive synthesis from Phoebe, and then modular synths from noise engineering. And then Nico showed us subtractive synthesis yesterday. And so this is where we are, by the way. So we are almost halfway through. So we're going to be covering FM synthesis on Friday, which is going to be Uche, and then we have special guest John Chowning, who invented FM synthesis, and that's going to be really fun and really special. And then our last lecture on just kind of sound is going to be about physical modeling of sound, so physically modeling sound systems and instruments. And then we're going to be switching right over to speech for the rest of the time, talking about synthesizing speech specifically. So let's talk about sampling. So who was able to follow the last couple of days? Good. Is like all this like open pipe, closed pipe, harmonics, foyer, whatever. I asked the question at the end of Nico's lecture, which is, why don't you just record a flute? Why don't you just record? Does anyone know why we didn't just start with like record, piano? Why did they start with all the kind of fancy electronic stuff? Yeah, recording technology was terrible for a very long time, especially digital recording technology. Doing things using recordings was hard. And so but now like we have really good computers and stuff. I want to do here, we're going to do something. I don't need to do any closed pipe, open pipe. See if I can really do this. Why did I do this earlier? Here, Cole, can you come for a second?
What do you mean, Jim?
Can you hold this button, and then while still holding it, press 8 and hold both of them?
Okay. Ready, set, go.
Let's try one more time. I didn't do a good job.
Ready, set, go.
Gridspace. Kevin, louder. All right. So the most important thing is I didn't need to do any math or even like that much computer stuff. But this is from Phoebe's presentation. There's a lot of different ways we can make sound on the computer. All of these are kind of like constructivists. Like we start from nothing, we start de novo, and we kind of think about how we think instruments work or sounds work, and we try to reproduce that maybe using, you know, a lot of math or a lot of thinking about how we think the system works. And that's great because you control it, you understand it, you can manipulate it. Yesterday, Nico showed a technique. He likened it to like additive versus subtractive art, right? Where you could, instead of trying to build something from scratch, you can start with something that's like harmonically rich and start to carve away that you sound you want, like you're making a statue, right? But there's a third approach, which is we can just extractively do it. We can just go into nature, go into the world, and collect sounds, which begs the question, like, why were we not always doing this? So just a quick review. I know Natalie covered this, as did Steven. So like imagine we were doing a weather station, right? We have temperature throughout the time of day, right? Temperature changes continuously. It's a real function, but we can sample it at different times and we get different results when we sample it, right? So here it looks like it's really high. Here it looks like it's really low. Here it looks like the temperature is going down. And so you need to sample enough that you capture whatever you care about, right? That's the important thing. This is an analog to digital converter, or one way to do an analog to digital converter. This allows us to turn something from some sort of sensor, like a condenser microphone or a MEMS sensor in my phone, into a digital signal like that. So an ADC slides along the signal and collects it, turning it into digital data. That's how we just made that, right? Instead of inventing all the samples, sample by sample by sample by sample, we just collect them at some sort of fixed rate. Or you could do something fancy like Steven showed with the variable sampling rate. And then you can reproduce that using the opposite. You know, if you take ADC and you move the letters around, you get a digital analog converter, and that does the opposite. And it allows you to reproduce that as sound from some sort of actuator, like a speaker. And there's a couple problems. One is you're quantizing your amplitude, right? You know, you can't use infinite bit precision for how loud something is at a given sample. So you have to quantize the amplitude. And you know, depending on your bit depth, you might lose different amounts of information that you care about. There's also time quantization, which Steven talked a lot about, which is we have to make a decision about how often we sample. So just like that weather station, if we don't sample enough, we're going to lose out on high frequencies that we care about for our music, right? And so, you know, how high do we need to sample? Well, that's the Nyquist frequency, right? So we don't have, so I don't Steven talked about aliasing, so I'm just going to go through this. We have to sample like this. We have to sample at twice our bandwidth. So human hearing goes up to about 20,000, depending on how old you are. And so you want to double that. Ideally, you would sample like around 40,000 to 44,000 if you want to completely reproduce the sound as you would have heard it. But that's kind of cool, though. You know, Nyquist and Shannon proved that you can actually reproduce the signal to the limits of your perception exactly using digital sampling, right? Meaning that when we record it using a digital sampling system, we can reproduce the sound as if it were generated live. We don't need to calculate it from scratch to generate those samples. We just play back maybe a professional instrumentalist playing that note some previous time, or whatever else we want to reproduce. Maybe we don't want to reproduce an instrument at all. And that's kind of a miracle, right? You can actually, using digital sampling, not need to generate anything or interpolate anything or figure anything out. Certainly not, calculate physical principles of vibrating objects or whatever. You can just replay the sound. The problem is, 40,000 samples per second, if you want to generate a full song, it gets really big quick. And that's why for a long time we had to, especially when we're building the first electronic instruments, do a lot of other things. And in the process, discovered a lot of really cool new ways to make sound, which we covered the last couple of days. But sometimes you actually just want to make a piano, and you want it to sound like a piano. And so here's the anti-aliasing filter. So the idea here is prevent aliasing. You need to make sure that you cut out frequencies above 20,000 hertz or whatever your Nyquist is, both on the input and then when you regenerate it. All right, so yeah, again, my question, why didn't we just start with sampling? We didn't start with sampling because, yeah, digital recording, really the ability to store data, especially in like RAM or in fast memory, like even at PROM, the ability to rapidly turn that into sound, you had very limited space. And certainly to store many samples from one instrument or from a recording on a hard drive, even not that long ago, was impossible. And so in lieu of using analog technology, there was no easy way to build instruments interactively out of recorded sounds. You could do it to a limited degree, which we'll talk about, but that's why we had to invent things like using oscillators and using filters to reconstruct sound using technology that was available at the time. And again, discovered really cool, awesome new sounds that didn't exist before, but also did a reasonable job at mimicking sounds from common instruments, which a lot of early electronic instrument artists were trying to do. Like Wendy Carlos was really just trying to mimic instruments, from an orchestra. Or when we see John Chowning tomorrow, similar deal. So the music that that we're playing before the lecture, that was an example of musique concrète, which was an early example of using tape loops and spliced tapes as an early form of sampling. There's actually a lot of examples of this, and if you look, at the history of a lot of different genres like ambient music or people like Brian Eno, of just using tape loops and analog tape systems to sample sounds, right? So splicing together very small amounts of sound as if you were doing it with a sampler. But it wasn't with like an interactive instrument. You had to actually cut tape or use specialized hardware to do that. And so, you had genres around starting to reuse recorded sounds in ways that, were non-intuitive. So sorry, this is mislabeled, but this is an example of one of the first analog synthesizers using tape loops. And then you finally got in 1979 the first digital sampling system, the Fairlight, and a lot of pop music used the Fairlight. This allowed you to start to build instruments that were sampled, but with very limited capability. By the 80s, you had several more, and then explosion of their use along with FM synthesis, which we'll talk about on Friday. Here's another example from 1986. These became ubiquitous in the 80s. As soon as we had the ability to sample instruments, it became easier to reproduce certain instrument sounds that were hard to synthesize from scratch. In the 90s, you started to have consumer software and free software like trackers, which is kind of, Nico likened the little coded mini MIDI that I built in the first lecture to kind of being like a simplified tracker, where that was often software using very short samples. There were like 1 million of these if you're around. David, you probably like them, actually. They're great. And then finally, with the emergence of sampling, you started to have controversy. This is like the most famous one, and it was actually the lawsuit that kind of set the precedent for how sampling could be used.
Yo, VIP. Let's kick it. Ice, ice, baby. Ice, baby. All right, stop. Collaborate and listen. I sit back with my brand new invention. Something that's a holding me tightly. Flow like a hawk, daily and nightly.
Who's a bigger fan of Vanilla Ice versus Queen? So like Vanilla Ice, Queen. All right. So, so Queen, David Bowie, they wrote a song Under Pressure, which was sampled by Vanilla Ice pretty directly. There was a lawsuit. Vanilla Ice lost. The limits of the ability to sample sounds from the environment, especially other commercial music, has, you know, obviously one has been like the foundation of like a lot of R&B and hip hop, and then later all music since the 1980s. And so the ability to actually use digital technology to rapidly sample other songs and then construct new songs from that has become the foundation of like half the genres of music that we listen to today. And it was all enabled by the ability to start to actually take little bits of sound from other songs and rapidly use them using digital technology instead of needing to actually like take a tape recording of it and splice it into, you know, or play it into your recording, right? Which, you know, opened up a lot of new opportunities artistically, but also like caused a lot of problems. All right, so next slide here. Now back to just like virtual instruments. If you want to sample so like a minute ago when I just like sampled that like recorder or the ocarina, and then I sampled like the Tibetan singing bowl or whatever, this simple sampler just kind of like pitch shifts the sample for each example and just reuses that one sample to build out a full instrument. You could do that, and that's what I did, and you can do that. Can anyone think of like problems with like just grabbing one sound and using it as basically the entire instrument?
The relation between what formants might be different as you change.
Yeah, like your harmonics are not going to shift linearly, you know, because, you know, our musical layout of notes is logarithmic. And so if you're linear shifting all the pitches, you're gonna have problems. There's ways around that. What are other problems?
You can't get like a slide on the guitar or something like that.
Yeah, so like articulations and transitions between notes. Oh yeah, people. Right, so the first answer from Uche was if you just pitch shift everything, the relationship between the fundamental and the harmonics is not going to change in the way that you want it to. And then Hull pointed out that, you know, things like a slide on a guitar and other articulations, glissandos, legatos, all those things are going to be lost or hard to reproduce as well. You see the same thing. And when we start talking about speech synthesis, you're going to see the same thing, where if you just recorded each phoneme individually and concatenated them together, there's actually things like diphthongs and ways that triphones interact with each other in a way that just gluing together phonemes doesn't work, right? Same thing happens in sound synthesis and music synthesis. Can anyone think of other issues? I have a long list of them later in the lecture. So.
Well, for example, guitar, every string entrance in the spectrum.
Yeah, so Stephen pointed out like the different string, the guitar has 6 strings, they have different spectra, some of them are coded in different ways, and they all have different fundamentals, which means that there's different properties of them. And also sometimes you have one that like buzzes and you want to catch that. So you're actually left with a pretty difficult challenge, which, you know, since the 1990s, I'd say has been maybe the dominant focus of a lot of commercial virtual instruments, which is just how to just reproduce a standard orchestral or musical instrument using virtual instruments. And to do that is a fairly painstaking job. So like here, let me switch over. Here's a virtual instrument for piano, right? This is just a piano. So, this piano has different samples for different velocities, for different notes, and it has multiple samples for the same note. This piano is 4 gigabytes. And so that's the reason that we only started recently being able to, you know, produce high fidelity sampled instruments. Here's a bell instrument. Again, gigabytes for this, right? Here's another bell instrument here we have, I think. That's for later. If we want to make a virtual instrument, there's a bunch of stuff. So timbre velocity dependence. So when you hit a note harder on different types of instruments, whether it's a brass instrument or string instrument, the timbre has a dependence on the intensity or the velocity, and it's a very subtle difference. So you have to record the instrument at many different velocities. If you just simply pitch shift, like we talked about when Uche answered, you have artifacts from pitch shifting. You also have memory constraints. Like you can't make these things infinitely big, no matter what your target hardware or software is. What does he have? Like Cole said, transitions, articulations, trills, glissados, slurs. Hey, Benson. There's no latency, right? So you need to be able to replay these samples interactively. And so if you have to load a ton of stuff from IO, that's not going to work. So you can't just load everything from your hard drive. You have to have things in memory or in a relatively fast memory store relative to the size. Otherwise, we're not going to make it interactive. Expressive redundancy around robin effects, like if you play the same note repeatedly, which is a common thing you might do with the instrument, if it sounds identical every time, that's different than a real instrument where so if like I play this bell multiple times, different every time, so you have to have multiple samples for the same intensity for the same note. There's also this is a hard one to model, but lack of sympathetic resonance between notes. So if I take this guitar and I play like the low E string, we'll say the low E string, and then I mute it. Other strings on the instrument, especially if it's like an acoustic, will still be ringing sympathetically because the low E string excited the other strings, right? And so there's this interaction between notes and other notes. So the previous notes you played might still be ringing on the instrument. And then there's environmental effects, like if you record. So if you go back to that piano, it's meant to sound like you're in a big grand concert hall. But there's some environment that you have to record the instrument in. Often it might be like a really dead environment, so you can then add other effects later. But you have to record it in a real environment. You have to choose a real microphone, right? You have to decide if you're going to use a condenser microphone or a ribbon microphone or whatever. And so once you do that, you can't undo it. And so rebuilding an instrument using sampling, required memory, DACs, ADCs, all to get to the point where you could actually believably do this, which really wasn't possible until the 80s and specialized hardware, and then 90s and 2000s for richer instruments. And even now, trying to actually reproduce these instruments with higher and higher fidelity remains a pretty active area of work. So it's a lot of work. It's just very different than all the math stuff that we were doing before, or using analog filters, or doing lots of DSP to do things. You're solving other systems issues, and then also just recording that sound in the first place, finding a performer, collecting all that data, organizing it, cleaning it up. There are simpler versions of sampling that came first, or are alternatives. Back in, I remember the early 90s, my sound card, I had a Sound Blaster. The Sound Blaster originally used FM synthesis, but later on, a lot of the later sound cards broadcast that they had wavetable synthesis. So your MIDI device could, maybe actually sound a little more real because it used like little samples. And so here's, by the way, an example of wavetable synthesis. Use little samples instead of, just generating everything using FM, which we'll talk about again on Friday. It turns out it actually wasn't properly using wavetable synthesis at the time. But the idea remains that, if you're deciding between do you want to sample or versus use synthesis, early 90s, we're at the point where sound cards were kind of at the cusp where you could kind of get away with trying to have hardware pre-built, for pre-built MIDI instruments, some sort of light sampling. But the way they did it was a lookup table for different instruments or different other inputs from the MIDI device. So, for the velocity, for the pitch, for the instrument number, look up what that little wave snippet is, something that is pseudo periodic, meaning that you can play it repeatedly if you need to, depending on the envelope. And so that's called wavetable synthesis. Now, wavetable synthesis is kind of cool because you saw a little bit of a version yesterday when Nico was showing on his mini log. He was showing that for the input signals, he had the ability to do like pulse width modulation, but also do it on like sawtooths and stuff. And it's not quite wavetable synthesis, but it could show how if you put a maybe interesting starting signal before you start hitting samples or other filters, you can do some interesting stuff. So this is an example of a wavetable synthesizer. And what's cool about it is that, because you're just storing a little periodic signal, you can have a really large library of them. A lot of times they have really interesting effects because they've maybe been generated using another method that we talked about, separately, and then have been cached so that you can use them. They're really performant. So here's like a brass sound. So let's see what else we got. We have steel. And you can sound. Here's a kind of formant sound. Lead sound. And so, yeah, you can actually do quite a lot like this. And so a lot of the kind of sampling-based, hardware devices and synthesizers from the 80s and 90s were often using really short samples and using them more akin to this kind of wavetable synthesis. And then into the 90s, a lot of sound cards and sound devices pretty much exclusively used, these lookup tables to quickly map between like a MIDI input signal and some sort of output signal, and then played it repeatedly, right? That was something that was possible to do with a small amount of memory. But it turns out, like a lot of the other techniques that we did, limitation is good for creativity, and so we invented lots of unique sounds that we now try to reproduce because either we remember them fondly or because there's no other way to make them. Another variation on sampling is granular synthesis. Granular synthesis is the idea here is that you have a starting waveform and you recognize that there's a rich source of data that you can sample from that one waveform. So I have like a starting waveform here that sounds like this. But from it, I can get a lot of really interesting effects. So I've sampled that, and I can cut it into little pieces in lots of different ways. You can even get these really glitchy sounds. Let me see if I can get one. And by stacking a lot of these, you can build really interesting sounds, just using like a sound from nature as a source of information to ultimately like build a more interesting soundscape. That's actually all I had today. I don't know if anyone had any questions or anything you guys want me to show.
What do you, what counts as a grain? Is it just a short sample of the original?
Yeah, a grain in granular synth is just a very small subsample of the original sound. And the idea is that you might extract hundreds of grains and then construct sounds from those grains. So there's many ways to do that. And you can build really, really complicated sounds using one waveform as your source. And in granular synthesis, it's kind of tricky to use, and it's tended to use to make very unnatural and glitchy sounds sometimes, but they're really cool.
In sampling, when they're choosing like a recording, is it like they'll choose the attack, decay, like is that recorded or is that more up to the user, like when they're recording?
Yeah, that's a good question. So that's a decision you have to make. So the question, by the way, for people listening in, is does a sampler typically apply an envelope to the sampled sound, or do you just use the original envelope? I mean, as we learned before, like, every instrument has a different decay property, and so it's a missed opportunity in some cases to apply your own envelope rather than use the natural one. So like, from earlier, let's see here, like my bell, could you, yeah. So in this case, like, we can just use the natural decay of the instrument without having to apply an envelope because it's got a very natural one. But if you had a continuous sound, or like in granular synthesis, where we're just going to be a very small region where the intensity has no envelope to it, it has an envelope generator built into that, virtual instrument. So That's how it's able to have that decay property as if it like had an envelope. But yeah, that said, you know, even on most samplers, you have the ability to make that decision. So if I take again this bell instrument, that's right. So we need to trim it. Can't remember how to do it, but there's a way to just trim the region, and same with like all the other synths that I was using. And so you can just, you know, grab a region that doesn't have any decay and then apply it on a little later, and, you know, which is kind of the idea of the granular synth. The MIT students want to see Benson. Hey, Benson, come. Benson, come here. Come on. Is there anything I didn't? Oh, by the way, I didn't cover formant synthesis because I thought Stephen covered it in tons of depth. So that was, I think, originally scheduled for this one. In terms of what's left, you know, just to take inventory. So, so far what we have left is FM synthesis, which is, you know, a very unique way to make a pretty wide variety of very exotic sounds. And then physical modeling, which we're going to talk about on Monday, which is where you actually model the physical instrument. There are other methods of synthesis. In fact, there's infinite ways that you can generate samples from a high-dimensional space. But where we're going, if it's not obvious, is neural synthesis. So if you're trying to build an instrument or some sort of system that just vibrates, you can everything from modeling it or try to reconstruct it or record it. But if you have to generate someone speaking, saying something that's never been said before on the fly, there's a very long history of trying to use a lot of these methods. And so John Chowning on Friday is going to talk about how they try to apply FM synthesis to build out formants. For speech synthesis, formants synthesis itself, like Stephen talked about, comes from the history of trying to generate speech. And all the problems we talked about with just concatenating phonemes together, transitions, intensity, modulation, not to mention the way that you express yourself through speech, those problems are magnified 100x with speech. And so what we're working towards is eventually neurosynthesis, where you use machine learning and data to produce something from scratch. And that can be equally applied to instruments. It can be equally applied to any sound system. That's not on the list of types of synthesis because we're gonna spend 2 weeks on it. But it turns out that if you want to produce speech and you need it to sound good, that's the only thing that seems to work. And it applies to instruments, it applies, you know, you can use it for anything else, but if you want to make speech, parametric methods, concatenative methods, formant synthesis, all of it did okay and sounded robotic, but it wasn't until we started using large, deep learning-based models that we were able to actually start to make something that sounded real and that can be done interactively like we do with our bots at Gridspace. So that's where we're headed. Again, FM synthesis with John Chowning is Friday, really special one, don't miss that. And then physical modeling, and then we move straight to speech. So we're gonna be talking about early speech methods the rest of next week, including a lecture just dedicated to pioneers of speech synthesis. So we're gonna have Sandy Disner from USC, we're going to have Gene France, who created the original TI chip for the Speak and Spell. And then we're going to be moving into neural methods the last week. So that's where things are headed. We're pretty pumped. Any last questions, by the way? Any remote questions?
I have a question about something vaguely related to Nico's lecture. What are transfer functions in filters and why do we care about them?
That's a good question. So the question is, what are transfer functions? What are filters? Why do we care about them? Do you actually not know, or are you just asking?
I literally don't know.
Yeah, cool. We probably should have and could have had a whole lecture on just filters. You know, we could add one. I don't know, Natalie. You would talk to Z transform, and yeah, so Natalie's volunteering to do it. If you guys couldn't hear, in general, if you have an input signal, so imagine like a step function, right? Or like a a sharp peak, like a delta function. There is an infinite number of ways that you could transform it through some sort of filter. In general, if you talk about maybe in Fourier space or using a Laplace transform, you talk about the ratio of like the input to the output in like, you know, frequency space. That's typically called the transfer function in like control theory and signals and systems. And it is really just a fancy way of saying, how are you remapping input frequencies to output frequencies? And filters can do a really large array of things. So like when Nico was showing, you know, subtractive synthesis yesterday, he talked about the, you know, and same with the filters that noise engineering were showing. You can have filters that have resonant frequencies that are often called poles. They're called poles because you tend to, in the transfer function, have a denominator that goes to 0 at certain frequencies. You know, and if you're, you know, if you study complex analysis, like those are the same type of poles that you have to integrate around when you're doing like Colton knows a lot of math. So, you know, if you're doing like a path integral or something, this means the same thing. And similarly, you might have zeros, a place where, you know, you actually lose all energy. And the reason that filters matter, so why do we care about filters? I mean, one, that's the whole name of the game with subtractive synthesis. Like all Nico was doing was applying filters to a really simple input signal to selectively and intelligently filter out frequencies and then maybe add feedback. So feedback is any place where the filter takes the output and puts it back into the input with maybe some sort of attenuation. And that's what ultimately can generate poles and zeros, you know, when you have that feedback. And everything that modulates a signal in the real world or in a digital signal chain has a transfer function. So like if you like are studying, you know, phonetics and speech, you know, you have the sound generated in your larynx and it's modulated, you know, by the whole rest of the system, including, you know, your ability to shape your, you know, the formants, you know, or the vocalized vowels, and also obviously the ability to generate other sounds on top of it, like fricatives and stuff. Similarly, you know, if you have a piano in a room and you want it to sound like there's here I can apply a filter to this piano actually. You want it to sound like you're in a cathedral, you know, you can apply some like some filter that basically acts like a reverb or room reverb, and that can, you know, obviously be very important to just getting the sound that you want. And then there's things like, yeah, low pass or high pass or band pass filter, where you just literally want to, for effect, add or remove certain filter here. That's right. And so it matters, yeah, because, you know, in general, like a lot of the effects that you want to generate, especially if you're trying to manipulate your sound, requires like one or many filters, you know, reverb and pass filters, and then on top of that, you know, signal conditioning obviously is also really important. Like you might have, you know, the buzzing from ground loops, and you might filter that out by filtering out like the mains power frequency, or, you know, you might want to filter because you want to use the filter as a source of energy itself, like Nico showed, with like a filter with so much feedback that it gets distorted. Same with like a guitar distortion effect, where, you know, you might actually overdrive it to the point where you're just clipping out an op amp, and that's actually the sound that you want, because there's so much feedback that it's, you know, even a very small input signal saturates in some really nonlinear way some filter, and, you know, that all produces, you know, sounds that you just can't reproduce any other way. Is that an answer? I don't know. Hey, Natalie, is that good?
Like, from what we learned, it's just, you know, sometimes you don't want things. Get rid of them. That's what the filter does. Sometimes you want things to be different, then put them through a filter. And doing all this in Fourier space simplifies it greatly, which is why it's so fun. It's like 8 years.
Any other things? All right, well, thanks guys. This was awesome. Join on Friday for FM synthesis with Uche, and with John Chowning. And we're super pumped, and then we'll be moving on to voice next week. So thanks everybody.